Alright, so last one we left off here, we had discovered that the diode was in fact going to be reverse biased, holding the 9 volts Zener rating, so minus 9 volts from C to D. We discovered that the final current for what we called loop A, which includes V1, R1, R2, R5, and R6. The final current was going to be, or will be, 23.97 milliamps. So that current, the same current for R1, R2, R5, and R6. The B loop was this right side loop. It includes the diode R3, V2, and R4. Okay, so the final current for that B loop is going to be 26.92 milliamps. So R3 and R4's final current will be 26.92 milliamps. Now, using node analysis, we were able to show that R5 entering into this node where D is, and then leaving over towards R4. So R5's current is lower than R4's current, so there must be some current coming in, and the only possible place is through that diode. And so the simple equation IB equals IA plus ID1, or ICD in this case. Okay, so basically the difference between IA and IB is the current that's traveling through that diode. In all currents in electron flow, we're going to say the currents are flowing from negative to positive. So as they flow through a component, they flow through from the more negative end to the more positive end. Pardon me. Alright, so now we can solve for now that we know the final currents, we can solve for the voltages of all the resistances. And then we can do a quick double check, and if it checks out, then we can solve the AB voltage, and that should be the final voltage that we need to solve for this circuit. And at that point, we'll know all the final values. Alright, so let's just go right ahead and get into it. So I'm going to start with the smaller of the two loops here. I've got my IB current, which is seen by two components. So I'm going to start there and just make sure that those numbers look good. And if they do, I'll just keep on going. Alright. So, using Ohm's law, VR3 equals IB times R3. VR3 equals 26.92 milliamps times 110 ohms. Alright, so I'm not able to show my calculator now. I'm having some difficulties with the application that I use, but if I say 26.92 milliamps times 110 ohms, I get 2.962 volts. 2.962 volts. Alright, so let's do that VR4. VR4 equals IB times R4. VR4 equals 26.92 milliamps again times 150 ohms this time. VR4 equals, okay, that same current, 23.97, no, that's the wrong one, 26.92 milliamps times 150 ohms, and I'm getting a value of 4.038 volts. Alright, so what I like to do just to make sure that I'm on track is I will quickly do a voltage loop equation just to verify that my voltages add up. So let's go ahead and do that. 0 volts equals, and I'm going to go start at point D here, go clockwise as I always do, plus 9 volts plus VR3 minus 16 volts and plus VR4. Now I found those two voltages, so plus 9 volts plus 2.962 volts minus 16 volts plus 4.038 volts. Alright, let's see how we did. So 9 volts plus 2.962 volts for VR3 minus 16 plus 4.038 volts. And I get a number very, very, very small. So I'm going to say rounding error, and it's pretty much 0. So 0 volts equals 0 volts. So my Kirchhoff worked out, and Kirchhoff is feeling good right now. Okay, so I'm going to now solve for those remaining components. All right. So I'm going to do R1, R2, R5, and R6, and then we'll double check again. Okay, so R1, VR1 equals IA times R1, VR1 equals 23.97 milliamps times 110 ohms. So VR1 equals, let me just punch that in, 23.97 milliamps times 110, 2.636 volts. Okay, I'm just going to box that one. Okay, VR2 equals IA times R2. VR2 equals 23.97 milliamps times 130 ohms. VR2 equals, okay, so I've got 23.97 milliamps times 130. I'm getting 3.116 volts. Alright. Now I'll just come over here. VR5 equals IA times R5. So VR5 equals, again, 23.97 milliamps times 220 ohms. VR5 equals 23.97 milliamps times 220 ohms gives me 5.273 volts. Alright, VR6 equals, again, IA times R6. VR6 equals 23.97 milliamps times 750 ohms. VR6 equals, let's see, 23.97 milliamps times 750 this time. That one's 17.98 volts. Alright, so we did a Kirchhoff double check of that loop before. We can now verify this loop. We can verify the outside loop. And if all those things check and our currents all check, then we know we've got all of our numbers right, and we just have to solve quickly for that AB voltage, which would be pretty easy at that point. Let's just do a double check really quick and see how that goes. So I've got my loop here. I'm going to just verify that same loop that I did for A. So minus 20, and then plus the resistors, minus that 9 volts. Let's see if I can do it. Okay. Alright, I'm going to run out of room, so let's go 0 equals minus 20 volts plus VR1 plus VR2 minus that 9 volts from that diode plus VR5 plus VR6. So let's just see what I just wrote here. Basically, it's going to cut off the screen, but minus 20 plus VR1 plus VR2, and then minus that known 9 volts plus VR5 plus VR6, and I'm right back where I started. Okay, let's go plug in those numbers and see how we do. 0 equals minus 20 volts plus VR1, which was 2.636 volts, plus VR2, which was 3.116 volts, minus 9 volts, plus 5.273 volts, plus 17.98 volts. Alright, let's see if 0 equals 0. So I'm going to type this right into my calculator. So minus 20 plus 2.636 plus 3.116 minus 9 plus 5.273 plus 17.98, and I'm getting 0, whether that's rounded or not. No, my calculator says that is 0, 0, 0. So Kirchhoff again, super happy. So that means we're happy because we know that so far our current nodes are good, because we solved these nodes using current analysis, and all of our voltages add up. The next question is, can we go around the outside and add these things up, which we should be able to. We've already double checked it to the nth degree, so it should be a simple matter to go around here minus. Alright, minus 20. Okay, so minus 20 plus VR1, which was 2.636, plus VR2, which is 3.116, plus VR3 now, which is 2.962, minus that 16 volts for V2, and then wrap back around to R4 plus VR4 4.038, and then over to R5, and we're hitting the plus side, so plus 5.273, and then finally back to VR6 plus 17.98, and I'm getting like 5 millivolts, so pretty much 0. That's just a little bit of rounding error. So Kirchhoff, super happy. I'm going to bring these numbers over to the final version of this circuit, and we're going to solve for AB, and we are done, which is a good feeling after all this.